Hey, this video is from Chapter 3, Section 2, and our topic is exponential and logistic modeling. What you'll learn about in this lesson: constant percentage rate in exponential functions, exponential growth and decay models, using regression to model population, and other logistic models. And why we're learning this: exponential functions model many types of unrestricted growth. Logistic functions model restricted growth, including the spread of disease and the spread of rumors. So constant percentage change. Suppose that a population is changing at a constant percentage rate R, where R is the percent rate of change expressed in decimal form. Then the population follows the pattern shown. So here on the left we have our time in years, and on the right we have our population. Now at time zero, something that you're going to want to get used to. Anytime we call time zero, that's always our initial condition, what we call our initial condition. And what you're going to see here in this case, population P, we have P sub 0. And we can also refer to that as P naught. Okay, P sub 0, P naught. So that is our initial population or our initial condition. And you can see here, and after 1 year, the value of the function at 1 is P naught plus P naught times R. So it's the initial population plus the change in the initial population, which is calculated from taking the initial population times the rate of increase. And so what we have here is we have P naught plus P naught times R. That can be simplified into P naught times the quantity 1 plus R. And so we can see a pattern develop here. We look at P of 2, that's P of 1 times the quantity 1 plus R. So we have P naught times the quantity 1 plus R squared. When time is 3, it's cubed, so on. So after a certain number of years, P of t equals P naught times the quantity 1 plus R to the t power. So that's the generalization of this behavior. So the exponential population model: if a population P is changing at a constant percentage rate R each year, then P of t equals P naught times the quantity 1 plus R to the t power. P naught is the initial population, R is expressed as a decimal, and t is time in years. So tell whether the population model P of t, which equals 786,543 times 1.021 to the t power, is an exponential growth function or exponential decay function, and find the constant percent rate of growth. What we have to do is we have to look right here at this value, 1.021. 1.021, we know from what we looked at in the last section, that's our B value, or our base. And what we were told was that when B was greater than 1, that meant that we had a growth model. So we know that we're going to be looking at a growth model here. Now what happens is when we have this 1.021, the 1 takes care of the growth. So really what we need to focus on is the 0.021. 0.021 as a percentage is 2.1%. So that's the growth rate of this population. Okay, anytime you want to calculate how much something has grown, and you know the growth rate, in this case if it was 2.1, you would multiply that by the factor of 1.021. So here's a slightly different explanation. Tell whether the given function P is an exponential growth or decay, because 1 plus R equals 1.21. So again, it's a slightly different explanation here. 1.021, when we break that up into 1 plus R, that would equal 1 plus 0.021. So the 0.021, again, like I explained in the previous slide, is your rate, or your growth rate. All right? And since that rate is greater than 0, we have what we call an exponential growth function. So determine the exponential function with initial value 10 increasing at a rate of 5% per year. Think about where do we insert, if you will, into the formula or the form, the initial value. Think about what we do with the rate and how we express that. And so the 10 is our P naught, our initial value. The rate is 5%, which we're going to write as 0.05. And we're going to add 1 to that. So the function is 10 times the quantity 1 plus 0.05 to the t power, and we can simplify this parentheses. So that would give us 10 times the value 1.05 to the t power. Again, if we are using this function to do calculations, we just have to be very aware, careful, especially if we're using a calculator to do this. We need to make sure that when we do this calculation, that 1.05 to the t power, whatever t happens to be, is calculated first before we multiply it by 10. So here's an example of modeling bacteria growth. Suppose a culture of 200 bacteria is put into a petri dish and the culture doubles every hour. Predict when the number of bacteria will be 350,000. So go ahead and think about that. Pause the video and try to work this out, and when you're ready, go ahead and play the video. Okay, so if we start off with a culture of 200 bacteria and it's doubling every hour, then the first, after 1 hour, the value is going to be 400. Okay, and then after another hour, it's going to be 800. And you can see what's happening. The trend here is that we're going to take 200 times 2 to the number of hours, power. So the general function in this population of bacteria is going to be 200 times 2 to the t. So how do we solve this? Well, we solve the equation 350,000 equals 200 times 2 to the t power. Divide both sides by 200, and then use your calculator for the rest. So we get a value of t equals 10.77, or about 10 hours and 46 minutes. So here's some data. Use the population data in the table to predict the population for the year 2000. Compare with the actual 2000 population of approximately 281 million people. So if you have your TI handy, it might be a good idea to go ahead and enter this data in and see if you can maybe try generating a scatter plot, generating the regression model, graphing both on the same graph, and see what you get. I'm going to have that for you here in just a moment. Remember, anytime we're working with years, we want to take our first year value, and that will be our initial year. So we will take years. If you want to use the letter x for the variable, x equals 0 represents 1890. So here's what the graph looks like when we generate the scatter plot and calculate the exponential regression model and graph that function on top of our scatter plot. You can see here that this is our regression equation, and so we can use that equation to calculate what we were asked to calculate. And if we go back here, we were asked to calculate the population in the year 2000. So what x value would represent the year 2000? Well, if we go by tens here, 1890, we go up by 10. This is 20, 30, 40, 50, 60, 70, 80, 90. So 1990 could be 100, and 110 would be our x value. So based on our model, we come up with a value of 308 million for a population. If we compare that to the actual population was 281 million. So this is an overestimate. But again, anytime we're using a regression model, we're not going to have an exact value. But this is off, I don't know if you think that 27 million is significantly off or not. I mean, that's a pretty good overestimate. And as you can see up here, we don't have any more data, but the curve, if the data were to continue in this manner here, the curve definitely seems to be increasing in this fashion. So we may, the further out that we go in our model, the more of an overestimate we may find. But for the data that we're given, our model is a pretty good fit. Okay, so one thing we can talk about is maximum sustainable population. Exponential growth is unrestricted, but population growth often is not. For many populations, the growth begins exponentially, but eventually slows and approaches the limit to growth called the maximum sustainable population. And there are other terms for this as well. So here's an example. A high school has 1,500 students. 5 students started a rumor which spreads logistically so that S of t equals 1,500, the population, divided by the quantity 1 plus 29 times e to the negative 0.9 t power. That models the number of students who have heard the rumor by the end of t days, where t equals 0 is the day the rumor begins to spread. So in part A, this is asking us, what's the value of the function when t equals 0? So what is s of 0? That's what it's asking us. And part B is asking us what t value gives us a function value of 1,000. So those are 2 calculations that we need to be able to do given this function. So part A, like I said, find the value of the function at 0, and if we calculate that, 50 students have heard the rumor by the end of the day, and here you can see the calculation involved with that. In part B, again, solve the equation 1,000 equals 1,500 divided by the quantity 1 plus 29 times e to the negative 0.9 t power. Solve that for t. And then when we do that, we get t is approximately 4.5. So 1,000 students have heard the rumor halfway through the 5th day. There are many applications of this exponential growth, and then in this last example, an exponential growth that turns into a logistic growth model.